Hi everyone, welcome to this week's video on G²CPU. This week's video is all about signal generation, how we can create our own signals on the GPU without taxing the CPU. Some of you might have already used the CPU bound blocks in LabVIEW to create your own custom waveforms, but when we are looking at high channel counts or at high data rates, these can actually tax the CPU so much that both on a component and on a system level, so component unit tests or system level system tests, they can affect perceived performance. So when we are testing our algorithms with simulated signals, we're not only checking are algorithms accurate enough, but also are they efficient enough to deal with what needs to be dealt with in time. So this is also a great use case of GPU computing. So as a resource to the developer, rather than adding it to your product that you're giving to your customer. So your developer can efficiently check if the code is working without accessing the hardware. So maybe the hardware is not yet ready, it's in a remote location, maybe the developer is just working from home. He can easily verify the performance of the system without more added costs. So how can we use the GPU here? Well, the GPU, a lot of systems, a lot of industrial systems have an embedded GPU on the CPU. So these are OpenCL GPUs that you can access with G²CPU. And yeah, they're available in most systems, so you don't always have a CUDA card available. What do you do then? Yeah, OpenCL. So how can we use OpenCL? Well, with G²CPU set backend, we can define the technology we want to use. There are several available. We have CUDA, we have the Intel 1 API, we have OpenCL and the CPU. In this case, we're going to use the OpenCL backends. Now, once that's done, we also need to tell G²CPU which device to use. This current laptop has an NVIDIA graphics card, which is also OpenCL compatible. It has the internal GPU baked into the CPU, as well as a simulation platform for an FPGA from Intel. Now, in my case, I know my internal GPU is set to device ID 1, but if you're not certain which ID you have to give, G²CPU comes with a couple of functions to see what is available. And in this case, G2CPU gets info string is going to give us all the information. Here you can see them all, and here I can clearly see, just use here is OpenCL, so I just need to use 1. Now, with that done, our system is configured to use the internal GPU, so perfect for system level testing. We can have a look and see, okay, how can we generate these signals? Within these examples, I'm first going to show you a simple analog sawtooth signal, a digital PWM signal where we can vary the duty cycle, and lastly, a multi-tone signal. Great to verify systems where we have digital filters and FFTs going on, and we want to verify, okay, what is its behavior. Jumping back to the sawtooths. In this example, we just define the amount of samples we want to use, and we also define how many samples does it take before the next period starts. Now, this sample count we provided to G²CPU range array. So G²CPU comes with a couple of functions, well, more than a couple actually, that allow us to create arrays on the GPU. So we don't have to, we no longer have to create them on the LabVIEW side. We can directly create them on the CPU, on the GPU, drastically reducing time. So we have ways to create noise arrays, both uniform and normal distributed. We can create range arrays, so these increments for each index going 0, 1, 2, 3, and so on. We can create constant arrays and many more. Now, in this case, like I said, we're using G²CPU, range array. So we provide sample count here. Now, this function actually checks here on the input how many values are within this cluster. So we can just use the bundle to create a cluster of 1, and it will put out a 1-dimensional array. Should we need a 2-dimensional array, 3-dimensional array, or 4-dimensional array, we can just increase the size of this bundle, add more elements to it, and during development time, this will increase so that you can immediately see native to LabVIEW what your data is doing or what your data is going to look like. Also, we provide it with a prototype of a single because I'm using single point precision. And yeah, so the G2CPU range array is going to provide a 1-dimensional array of floating point 32 values, which are constantly incrementing for each index. G2CPU or G²CPU also comes with a ton of probes available for you. These not only show you the values, but also show you on which technology the array is being used. So in this case, it's OpenCL. We can see on which device it's running. And also we can see, okay, what other devices are available on the specific technology. We can show the table, and here you can clearly see 0, 1, 2, 3, and so on. Or we can have a look at the graph, and you can clearly see it's a straight line which keeps on increasing for the amount of samples that we've defined. Now, with that done, we've created our constantly increasing array. We can just ask for the remainder, so we're dividing it by the samples per period and using the remainder further in our signal or in our calculation or our algorithm. So what we're going to get here is a nice sawtooth signal, but some of you might already see the amplitude is all wrong. The amplitude is dependent on the value of our period. That's not what we want. We want the amplitude to stay the same while we're playing with this period. So next thing we have to do is normalize our signal. This can be to 1, this can be to another value. For this example, I just normalize it to 1. G²CPU comes with a ton of functions to get information on your signal. The one we're going to use here is max index. What this is going to do is it's going to search for the maximum value in the array for each dimension. Now in this case it's only 1 dimension, but it will give us a max value as well as an index or the location where it is found. Now because it's a range array, it just keeps on going up, so it's pretty much the same thing. But because we're not using that, we're going to say, hey, please release the index array, otherwise we have a memory leak. Most functions, they automatically release the array that you put into it, unless you specifically define, please do not release it, like is being done here in the max index 1D with this auto release set to false, because as you can see here, this array is still going to be used with the G²CPU divide function. But okay, we have our maximum value, which is the same as our index. And now we can say, hey, divide our generated sawtooths by the maximum value, which gives us a nicely normalized array or an array that's nicely normalized to 1. Great. Next thing that we can do is, well, have a look at digital signals. Now, the digital signal actually does not differ that much from the sawtooth signal, for PWM at least. This is actually how it's also created in analog circuits, by the way. But what's going to happen is, well, we're creating a sawtooth, so a range array, remainder, and then normalizing it. But then we're going to compare it to the fraction. If it's larger than the fraction, it's going to be a true. If it's lower than the fraction, it's going to be a false. But as you can clearly see here, we can play with it and see the PWM behavior is changing. The only thing that we need to take care of is the output here is a Boolean, because this is expecting a floating point. I did a conversion to floating point 32. You do not need a function like bool to 0 or 1 in G2CPU. Just casting it is fine. The rest will be taken care of for you. And then afterwards, of course, we can download it to visualize it here in LabVIEW. Now, the last signal is quite interesting, and that's the analog multitone. So most of the times we don't want a sawtooth. We don't want a simple PWM. We want to have multiple signals that we want to merge together to get a more complex signal. So for that, we can use the G2CPU range array once again, but instead of using a one-dimensional array, we're going to actually create a two-dimensional array. So we're going to make several sine waves that we then are going to merge together. So we create we're going to create an array of size sample counts, as well as of size of the amount of multipliers that we have here. So currently we have 4 multipliers, which means we're going to have 4 sine waves. We create our two-dimensional array. We also define in which direction we want it to increment. So we don't want it to go 0, 1, 2, 3 for everything, but rather up to down. So if we look here, we can clearly see it goes in this direction. Should this have been 0, it would have gone in this direction, going 0, 1, 2, 3. Okay, next up what we're going to do is we're going to multiply our two-dimensional array with a one-dimensional array. So in G2CPU, you can actually multiply arrays of different sizes. And what's actually going to happen is the array, or the lower counts array, so in this case the one-dimensional array, is going to be transposed over the two-dimensional array. What that means here is for each value here is going to be interpreted as a scalar for an entire row. So if we look here, we can see, okay, we have one column here being multiplied with 100u, one column here multiplied with 10u, 5u, and so on. We're doing this because we want to precondition the signal for a sine wave. So with this, we can actually define the frequency of the sine wave. So if we do that, if we then check the sine wave, just quickly putting in a probe, we can see, well, based on this signal, just taking the sine wave out of it, we see we have a high frequency signal, and the lower the multiplier is, the lower the frequency actually is. So high frequency all the way down to low frequency. Now with that, we have our several frequencies of our multitone. One last thing that we need to do before merging them together is saying, hey, multiply them with specific amplitude. So some tones need to be a higher amplitude, some tones need to be a lower amplitude. So again, we are doing a two-dimensional array times a one-dimensional array to get to change the amplitude of the differing sine waves, as you can see here. Next up, what we're going to do is we're going to take the sum. So the sum, there's a sum also. We're taking the sum of the entire array, no matter how many dimensions it has. But we also have an option to do it in one dimension. So we can say, hey, take these values together as we go forward. So in this case, rather than taking the 2 million samples and taking some of those, we want to take the sum at each moment in time of all differing sine waves. So that's going to be simply in this way, taking a row bound sum. You have the option here to add a sequential dimension like here, but for us it's the default is 0, so it's fine. But yeah, we take the sum, and well, we get the signal that we see here on the outputs. So this works for smaller signals, this works for bigger signals. You can even use this with the by key values or by key functions to even split it up to create compound functions. You can do so many different things. So yeah, this is barely scratching the surface. All I can say is play with it. There's so many things you can do with it, going from really simple functions, simple sine waves, to incredibly complex functions. So that's the end of this example. I hope you find it interesting. See you next week. If you want to see anything more, if you have any requests, feel free to ask me. And as always, G²CPU, it has both a commercial edition as well as a free community edition for you to download. Thank you very much, and see you next week. Bye!